Hello and welcome everyone. Thank you for joining us today. My name is Alyssa Tay and I'm with the Collaborative for Health and Environment, also known as CHE. I'm going to get us started with some quick housekeeping items. This webinar is hosted by the EDC Strategies Partnership. The partnership members include Healthy Environment and Endocrine Disruptor Strategies, or HEEDS, which is a program of environmental health sciences, Commonweal's Biomonitoring Resource Center, the Health and Environment Alliance, or HEAL, and CHE. We invite you to type your questions in the Q&A box at any point, and we'll get to as many comments and questions as we can after the presentation. If you'd like to activate closed captions, you can do that by clicking the button at the bottom of your screen. This webinar is being recorded and it's scheduled to last for an hour. If you'd like to download the slides, please visit the webinar page on our website at healthandenvironment.org. We'll put that direct link into the chat now. I'll now hand it over to our moderator, Charles Patton, Director of the Biomonitoring Resource Center. Charles.
Welcome, everyone. I'm really excited about this webinar. It's really, really important. We're going to be talking about TFA, trifluoroacetic acid. I don't want to go into detail with this because we have the most extraordinary speaker today. It's Hans-Peter Heinrich Arp, who is a professor in environmental chemistry at the Norwegian University of Science and Technology and senior researcher at the Norwegian Geotechnical Institute in Oslo, Norway. He's the author of something like 125 publications and has worked with many researchers as well to look at PFAS and try to figure out what can we do these days to stop the toxification of the biosphere. He's very serious, very smart, and please go ahead and let's take a look at your slides, Peter, so we can ask you many probing questions. Really excited about this. Thank you.
Oh, thank you so much, Charles, and thank you very much for this invitation. It's a pleasure to speak to this crowd with this, what I think is a very important topic and an urgent topic, and I hope to maybe shed some light and answer some questions you might have. So let's get right into it, and I want to start with just a precautionary tale that is relevant. So on the screen now, I am showing James Lovelock, who is one of the original or the founders of the field of environmental chemistry. And one of his great contributions was he invented something called the electron capture detector, which was able to detect chlorofluorocarbons that were being put into the atmosphere. And with this new technique, he would go around and he would monitor CFCs. But he didn't recognize any particular harm from the CFCs he was measuring. He was even quoted of saying there's no conceivable hazard of CFCs, it's just good to get the data. But then, of course, the hazard was realized. It was the destruction of the Earth's ozone layer. So later, this was not realized at the time when he was measuring, but then he had to backtrack that a little and say there was no conceivable toxic hazard. And of course, the discovery that CFCs, through putting these molecules up into the stratosphere where they would release chlorine and start a catalytic reaction that would destroy the ozone, letting harmful UV light clean the planet. We had the Montreal Protocol to stop the process. And I don't think it's talked about enough how much we really dodged a bullet. And then by a bullet, I mean a bullet to everyone, because current projections are that if the Montreal Protocol did not happen and we continue to do CFCs, by 2050, there would be essentially no ozone left, which would also mean the end of photosynthesis on the planet. So it shows many things, I think, this story. It shows how we can miss seeing early warning signs. It shows how fragile our Earth can be when we put chemicals there that accumulate and can cause such a reaction on a planetary scale. But it also shows how we together, once we recognize the solution and hopefully early enough, can work globally to do something about that. And this worked on the graph now. It's showing the consumption of ozone depleting substances since 1986, and it's been decreasing. So we have much less now. So this is a success story of good environmental policy. But the story with the Montreal Protocol does not end there. So where our story begins, or where I'll begin this story, is what we ended up replacing chlorofluorocarbons with. So the very first replacements that they put right on the market were hydrochlorofluorocarbons. And these were what they call drop-in substitutes because they were compatible with, say, the same type of refrigeration systems. You didn't have to change the technology. You just had to change the chemical. And so there was a shift that industry could rapidly make and put in there. These were better than the CFCs, but they still had chlorine in them. They could still lead to ozone depletion. And also they were greenhouse gases. So the Montreal Protocol, that they meet regularly or semi-regularly. And now they said, no, we need a third generation of refrigerants. And then they said, let's just use saturated hydrofluorocarbons or HFCs. And these were used, but then this was like one thing's better. There's no ozone depletion. But these were greenhouse gases. And also some people it was also discussed that they're going to form this, what is the subject of the webinar today, trifluoroacetic acid at some yields. So for every 100 molecules of this example refrigerant, this is just one of many, there would be 7 to 23 molecules of the TFA produced. And there was some concern about this because they recognized that this was extremely persistent and mobile in the environment. So it's not going to break down. It will just accumulate for every molecule we put out there. That was recognized early. And so that was a concern, and they did some work on that originally, but it was originally like, yeah, the risk is not so high. And so, but now they get to the 4th generation of after the Kigali Amendment, where they said, well, let's make now refrigerants that don't have this global warming potential. And so now they use these unsaturated hydrofluoroolefins. So they check the box of the low global warming potential, but now the ones that they're using in large volumes, like the one I put on the screen here, this HFC 1234YF, that's forming more TFA. It's forming TFA at 100%. And I said it's accumulating, and we got a lot of evidence that it's accumulating. So we see it accumulating everywhere, largely coinciding with the F-gas use following the Montreal Protocol. So this is now a famous study looking at Arctic ice cores. So these were an ice cores, like you can date them, so you know what year the ice was formed. And then you can see around the timeline of the Montreal Protocol, we got this huge surge in Arctic areas of trifluoroacetic acid, and to a lesser extent, much lesser extent, other short-chain PFAS. But it's not only ice cores. We see this also in trees. It's an extremely mobile compound that is able to go up the complete xylem of a tree and accumulate, or phlegm of a tree, and accurately accumulate in the needles. So this was a study where they took historically preserved biosamples of trees from different years, so they could do a nice control study. And they found in various species of trees, the TFA was rapidly accumulating. It's also rapidly accumulating in groundwater. And this can be surprising to some because one would think groundwater is usually a very clean source of water. It should be clean and it should be protected. But we are seeing rapidly rising concentrations of TFA also in groundwater. And it's enough so that we can even start using markers like this to age environmental samples. And I can go on. I mean, one of the interesting things I find, it's in everything we drink. We talk about groundwater, but we can also talk about wine. So this was some data that was recently shared with me by Michael Miller and Freiburg University. But we also see in aged bottles of wine, we got this increase in TFA, and it's also the minimum concentration that you might find in a bottle in any given year is increasing. So the background is increasing, and some might have more than others due to local sources. But pretty much, and we can go on, we can look at drinking water, tap water. So most of the concern about TFA is about the current concentrations in tap water, what we drink. But I think it's also important to keep in mind, compared to the other plant-based beverages that we're drinking, like wine, it actually has less concentration because of this ability to accumulate in all the plants. So if you're drinking tea, you'll have more concentration of TFA than the water you made it with. Beer the same, orange juice the same, apple juice the same. So pretty much if you want to drink anything that's TFA free, you'll either have to find some very old groundwater or a very old bottle of wine. And should anybody in the audience have access to old bottles of wine, please get in contact with me for research purposes. But now this is just a new phenomenon. It's a real thing to look at now, because now that we know it's accumulating everywhere, essentially anything that you can measure TFA in, you will find it. And what we did in this recent publication that was a critical review of the data that was out there was just to see how much of this accumulation we can see and where it's increasing. And on the screen here is the green bars are the concentrations before 2010, and the red bars are the concentration after 2010. So the bars are actually the maximum concentration in different things like rain and rivers and the ocean and ice cores. And then the dots are the median concentration in those media. But you see in all the media, the mean and the maximum, they're all increasing. And we found this break. Why do we have this break between 2010 and after 2010? The reason was before 2010, people were monitoring for TFA mainly in relation to the Montreal Protocol. But then when there was more somehow consensus that this was not a problem, the monitoring data dropped off. And recently, only in the past, mainly the past 5 years, people started to measure this again because they included TFA in their PFAS monitoring programs. But I'll just highlight one liquid media we should talk more about, and that's our blood. So these are two studies of the TFA that's in blood. So there's a Chinese study where they found blood in 97% of the people that they sampled with a median concentration of 8.5 micrograms per liter. And a key observation there was that TFA alone was similar to the level of all the other bioaccumulative PFAS combined. The same thing happened in a USA study where they found 74% detection with a median of 6.0 micrograms per liter. And this median was twice the levels of the sum of all the long chain bioaccumulative PFAS combined. And so this is just interesting. It's just because we're eating it every day. We are drinking it every day and in increasing quantities every day. It doesn't matter that it's not bioaccumulative. It doesn't matter that we excrete it rapidly. It's increasing in our blood and therefore in all our organs and all our cells. So I think it's a reasonable question to ask. What levels of TFA will be in the blood of future generations? And what will the impact of this be? So with that, that was actually just my introduction. So this is what I'm going to talk about. I'm going to talk about the sources of TFA, the irreversible effects of TFA, and then I'll move on to solutions, because even though I'm maybe scaring some of you out there, I am always focused on solutions, I want to know how to get out of this. So now we'll talk about sources. And I talked about one, refrigerants and blowing agents, but there's actually many other sources, and it's important to talk about those too. It's not just the refrigerants, believe it or not, but I'll go into them. But I'll start with this one I have in the corner here about there being no natural sources, because I think this is an important one to debunk. So part of the reason why in the Montreal Protocol, they originally thought that TFA was not a big concern was because some measurements in the deep ocean that found TFA. And then there was some kind of conclusion, well, this cannot be coming from us, from man. There must be some natural source of TFA down there, such as a hydrothermal vent or something. But this hypothesis, even though it's still around, and a lot of people refer to TFA as a natural chemical, it is not. We have no direct evidence of any mechanistic formation of TFA. We see no TFA gradients by deep sea vents. We do see other persistent chemicals like other PFAS, like PCBs in the deep sea. And we know now how they can get there. So these results that were surprising in 2000, 2005 are not surprising now. We know that chemicals, including plastics, including PFAS, can get that deep due to oceanic currents, due to the sinking of dense water formed on continental ice shelves, through marine snow deposition. And it's also this whole natural thing. It's not consistent with the time trends we're observing. So even if you were to account for TFA having some natural source somewhere, this does not explain the rapid explosion, the concentrations of everything we can measure. So let's just put that one to bed and talk about the real sources of TFA. Okay, so I talked about refrigerants. I'll just say another one because this is about the future, what we're going to be exposed to. So if you recall, I had this earlier slide. The top line is this TFA that we're phasing out because it's global warming, and the bottom one is the one we're going to use more of. And what you can see here is the projections, and this is just the projections for the EU 28 countries. I don't know the projections for America or other regions of the world, but this is for the EU countries, and this will see a rapid increase. And so we will expect a lot more accumulation of TFA in future than we're observing now. The rain concentration should increase by a factor of 5 or more by 2040. And you have to recall that each year it falls down. This is more TFA accumulating in everything, including our blood. And we're starting to get more data in there, and we understand how it works. So for instance, we can see if you look at this is a German study where they looked at TFA and rain over a year, and you see that the levels are highest in the summer. And here's also a more recent study looking at the daily cycles of TFA, and they get higher in the daytime. What this means that there's more TFA being produced when there's more energy and more sun means that the source is a precursor. So we can kind of rule out this is just the TFA molecule going up in the air and coming down. This is formed in the atmosphere from various precursors. So now we go to another source, and that's pesticides and herbicide precursors. And so recently there's been some mapping, and I have some major precursors of TFA on the bottom. So in Europe, it's flufenacet and oxyflorphin. They have this little CF3 group, but through biodegradational processes, they will release this CF3 group and form TFA. And in America, it's trifluoroalkyl and flumeteron. These are all primarily herbicides. And these were projections of how much TFA, based on where the major precursors are being applied, is actually entering the soil, and after that, the groundwater. So pesticides is definitely a reason that's being used to account for very high groundwater concentrations, higher than you'd expect to just the rain from the refrigerants breaking down in the atmosphere. There's also many pharmaceuticals that are being used. So these are some examples of some high volume pharmaceuticals that are on the market. So this biacalutamide for prostate cancer, fluoxetine, better known as Prozac, this will also degrade from TFA in the environment. I don't think I have to read them all, but you just have to think that this is also an agricultural chemical, because in many parts of the world, these will go through the body. They'll end up in the sludge or the biosolids that might be put on a field. And this would also contribute to the growing TFA that we might see in the groundwater of agricultural areas. We also have release from PFAS production and products. So the actual factories where they're making PFAS, that is actually where we find the highest concentration, certainly the hotspots. So first, there is a TFA produced in Europe. We know it's between 100 and 1,000 tons per year. So the direct production is usually used probably for selling for other products and other applications. But if also if a company was making this pharmaceutical or a pesticide, they might have using that as a reagent, and they might not register the tonnage. So there's also production there, but we get definitely releases where they're making these F-gas gases. There's very high TFA concentrations around those areas. They're very high around fluoropolymer factories, like where they make Teflon and things like that, and PFAS production, such as the river Arias in southern France. They have concentrations of 7,500 micrograms per liter, which is about 7,500 times you typically see. But also they will leach from products. So this was a recent study that just looked at different fluoropolymers they're using in the lab. And they find that they would get TFA coming out of the plastics themselves, also contributing to TFA in the environment. And interestingly, it wasn't only the fluoropolymers, also polymers would also leach TFA as well, used probably somewhere in the facility where they made these the plastics themselves, like in the molding or something like this. And I want to mention that water treatment and all the treatment we're doing, you know, if you're just thinking, oh, well, we can buy a filter and clean this from our water. No, we can't. TFA is so mobile that it goes through granulated activated carbon quite nicely. It even goes through most ion exchange resins. There's a lot of work on exchange resins to make them more efficient for TFA. And you might find that there's some theoretical ones out there, but there's no good filter methods for that. And then we can go on to the destructive methods that some water treatment facilities might have, like they might ozonate their water, they might chlorinate their water. And what that actually does, that might actually lead to higher TFA formation, because the pharmaceuticals and the pesticides and the other PFAS that are in the water, they might react in these processes, and one of the byproducts is TFA. So then you get remediation itself, increasing the TFA concentration. The only thing that we have that really works for getting TFA is reverse osmosis, which essentially collects all the ionic species, the salts, and in this case, the TFA from the water, and makes a rich brine. But that does not really destroy the PFAS. It's only putting that in the brine. And a lot of places I've seen, including California, that make brine from their groundwater, just throw that back into the ocean. So it's not really, it's just being moved. It's not really being treated. And the only way to treat it is if you do something very expensive, such as supercritical water oxidation or something like that. So this just leads to something that we say, like the absurd costs of TFA remediation. So earlier, I, with Professor Ali Ling from the University of St. Paul, I might have got the affiliation wrong, but we worked together with the Forever Pollution Project, which is a group of journalists in Europe that is centered around Le Monde. And it was really interesting working with them, because journalists, I found, are very good at collecting data from people very fast. But we were working with them, and we were trying to, and they had a project to map where they think the contaminated PFAS sites of Europe are. And then the next step was to try to figure out how much it would cost to remediate them. And from our estimates, like where we think TFA pollution could be and other short-chain PFAS, and remediating them from soil and water, it would cost 100 billion euros a year to keep the drinking water free using reverse osmosis and supercritical water oxidation. But it would make the water more expensive, no longer mineral. And we still have to remember that the wine might still have a lot of TFA in it. So how much would that really be reducing the exposure? Okay, so that wasn't so good. Oh, now I'm going to talk about something worse. And this is about the irreversible effects. What does this mean that we have this increase in TFA concentration? So I'm going to talk about these different media, and there's a lot we don't know about the effects of TFA, because it's accumulating everywhere, and we haven't measured the effects in everything, which we would literally have to do. But we have some data, so I'll talk about that. And this data is important, especially here now in Europe. So the first is the toxicity to mammals. And so what I'm showing here, and this is just, I'm just highlighting this study because it's important now, especially with European regulations. So this was a chronic toxicity study for feeding in rats. And what they were looking at is how the liver weights of the rats would change due to different exposures of TFA. So if you look at all these graphs over here, it's overwhelming, but basically on the y-axis, they're going up, that is the liver weights, and on the x-axis, the independent variable is the PFAS concentration. So they're just trying to see when does that cause an increase in liver weight. And based on this and other data, they can compare the relative liver toxicity or hepatotoxicity of different PFAS to each other. And so what they find with TFA, that's down on the corner here, it is one of the least toxic of the PFAS, but toxic nevertheless. They quantify it as 0.002 as toxic as one of the most toxic PFAS, PFOA. So that's 0.2% is toxic. And through what they derive, what we consider as safe levels in Europe, based on safe PFOA levels, they would derive a concentration of 2.2 micrograms per liters. And this is the recommendation in the Netherlands. And what we see in the Netherlands and other places that this level is already exceeded. Another study that has been making a lot of waves is a study on rabbits. So when they exposed rabbits to TFA, they found it had an effect on the embryos, and that there was a higher occurrence of folded retina and absent aqueous vitreous humor above the control range data, which would give it a classification as presumed human reproductive toxicants, which would meaning that it could at certain levels it would harm the offspring of mammals, and this would have regulatory implications, particularly in Europe. Now, there's so much we don't know about TFA, and this is why I find it so alarming that it's accumulating in so many other things. So if you go back to some earlier studies, this was about looking at what's happening to like microbial communities being exposed to TFA. And what these researchers did, and I'm just shocked that nobody followed up on this, but what they did was they took a special kind of TFA and they also used acetic acid, which is the vinegar, in other words, which is the non-fluorinated version of TFA. And they put a radial label on it, so 14 carbon. And when they do that, they can see where in the microbes or what part of the cells in the microbes does the TFA accumulate. And what they could find through two different studies is that the TFA is actually incorporated into the biomolecules in the cells. So it actually becomes part of the structure of the lipids, of the proteins, of other parts of the cells. And they could also show this when they compare it to living and dead cells. But this has not been followed up on. I'm trying to get the biochemistry community interested in this, saying what is going on here. Now, you might also be thinking, oh, but it's reacting now. So is this, maybe it's reducing in concentration because it's reacting with our cells, including the cells in our body and the cells in our gut. But you have to remember that our bacteria, our cells are biodegradable, TFA is not. So these would also automatically go back to just TFA to interact with something else, the next cell in the process. And now, speaking of microbes, let's talk about aquatic ecosystems. So the lowest no observable effect concentration, where they saw an effect on an algae community, and this was known since 1999. This is industry data. They found the lowest effect was at 120 micrograms per liter. And usually, since you don't really have the full ecosystem, you might take an assessment factor to reduce PNEX, what the effect concentration could be for other algae. And some people use values already as low as 0.12 to 12 micrograms per liter, which already puts us into the current range of TFA we're experiencing today. REACH used a higher study. They found an algal growth rate concentration effect at 5,600 micrograms per liter, which we might see near the hotspots. But if you put a PNEC on it, an assessment factor, what other the effects that could have in algae growth, we're getting into also levels that we see we're reaching in the environment. So, but I have to say, with all the toxicity studies, something that we have to think about is these are usually done on the scale of months, maybe 1 month, maybe 3 months. The thing with TFA is every organism is now exposed to it its entire life, and through the whole life cycles. And we do not have any data on what impact that has with such lifelong exposure. And finally, I'll go to soils and terrestrial systems, and you might recall the ability of TFA to accumulate in in plants. So we don't know what effects that might have on different plant species, but we can say there is a no observable effect concentration for plant shoot growth. So we do know at certain high concentrations, the plants do not grow as well, and it bioaccumulates in the plants. And there is also a very limited amount of data, but some data showing how TFA can affect various soil properties, such as soil pH, microbial respiration. Again, the microbes, what effect does it have on the microbes in the soil? Don't really know, but we can see that there's already effects where it would lower the microbial respiration and the bacterial abundance and the ability of soil to decompose litter, like leaves. This will happen up to, in this range, effects were noticed, and at higher levels than this, TFA, the acid properties take over, because TFA is also a strong acid, which you will encounter at very high concentrations. But there's very little data on these soil nutritional systems, and we should have them considering that they're accumulating in so many plants. So that's why I concluded in this paper that is highlighted here that it meets the criteria of a planetary boundary threat. So what is a planetary boundary threat? And I'm looking at time. Okay, what is a planetary boundary threat? Basically, you can think of that as changes we might make to the homeostasis of the Earth, from which we would depart from the Holocene from which the human race has evolved. This and chlorofluorocarbons would be an example of that, because they would have destroyed photosynthesis. That would have been a new age. But for novel entities like TFA, there's 3 criteria to say if it's a threat. Like, I'm not saying that we know where this boundary is, but we know that it could pose a threat. And one of them is that the pollution disrupts a vital Earth system process of which we are ignorant. And we are ignorant of a lot of the facts of the TFA, but we do know that there's probably more than we know of, because we do know of some already now. So this is an issue. So this condition is met. The second one is that the disruptive effect is not discovered until manifested at a global scale. This is what we're realizing, because it is increasing in every country all around the world. It's in the Arctic ice cores. So this is a global issue. And the third one is that the impacts are poorly reversible, because the level of pollution cannot be readily reduced. And this is especially true with TFA. It itself is persistent. And even if we say, okay, let's ban what we know tomorrow, like the fluorinated gases that are causing TFA, there's so much stockpiles out there integrated in our chemicals, in our cells, and everything else, that concentrations will still increase, and then they'll just be stable. Okay, now I'll try to lighten the mood and talk about solutions. So first thing that's important is with policy is to firmly declare that TFA is a PFAS, and it should be regulated like a PFAS. TFA is considered a PFAS by the OECD, and there's a scientific consensus that it should be classified as a PFAS. It's structurally similar to a PFAS, and there's a Google document down here. It's a PDF, but you can see that over 170 scientists have said we have to affirm that TFA is a PFAS and should be treated as such. It is by the EU. It is by 23 American states, but I heard this gentleman in the corner, Senator Tom Carper, he says that it should be excluded from the PFAS definition. And there's also a US EPA draft definition that's still around. It's still in the books, that would not include TFA in the definition, but we should treat it like that. The other one is there is a solution to F-gases used as refrigerants. So this is the so-called 5th generation of the Montreal Protocol. If we want the Montreal Protocol to have a happy ending, then we should use this 5th generation, which is free of TFA precursors. And there was a review done recently by one of my co-authors on the paper that we're highlighting, Juliana Gluga and colleagues, Jan Cousins and Martin Scheringer. There were 3 co-authors. They were looking at the technological readiness and availability of replacements to various types of heating and refrigeration technology that avoid the use of creating TFA. So you can see that for more information. Another one is TFA. There's also F-gases used as blowing agents. I didn't give examples of that, but you might encounter like polyurethane foams, which can also be used in refrigerators, or expanded polystyrene. They're nice and bubbly, but it's F-gases are also used to make those bubbles. But there are replacements to those as well, both to make those bubbles in polyurethane and polystyrene. And there's also alternative materials to that, which are also foamy and do not lead to PFAS. And this will be included in the PhD thesis that will be defended in a couple of weeks by Romain Figuer from the Stockholm University. He's on the 0PM project, and he's done a lot of great work on this. For pesticides and pharmaceuticals, there's the easiest thing there is to consider TFA precursor for pesticides being as a reason to not renew that the drug or the pesticide can be used. So as a positive example for this, there's a draft regulation coming now that they'll probably ban or not renew the license to apply flufenacet in the European Union. So it will likely go through, also because flufenacet was found to be an endocrine disrupting chemical in addition to a TFA precursor. And this is one of the major sources of TFA in groundwater. So that's happy. And then arfluorinated drugs, PFAS. So there's this concept of green pharmacy. It's a tricky issue, but we have to at least start to have that conversation. Can the innovation in the pharmaceutical industry find a path to avoid making these chemicals that release TFA? Can they find ones that are equally effective? I know this is a complicated thing, but we have to have that conversation of green pharmacy. And maybe also there's several examples that we could go through now to look at the different drugs. And if there's one that does not give TFA, maybe that should be favored in prescriptions or by health insurance companies over the one with TFA. And also just about restricting PFAS, because the production of PFAS is also a source of TFA. So this webinar is being organized by a California organization. So they have California Senate Bill 903, which is going to prohibit PFAS entering certain food packaging in the European Union and area. Where I'm based, they have a broad PFAS restriction proposal where they're trying to eliminate PFAS from many industrial uses. So this will also help eliminate TFA. And some tools that as part of my research project that I'm leading called 0PM, where we're looking at ways of exploring zero pollution of persistent mobile substances. We do have resources for people. One is made by our partners ChemSec, who made this PFAS guide, because we find that a lot of companies and businesses don't know if they're using PFAS or not, or some of the widgets or doodads they buy to make their products have PFAS. So we made a guide to help them find it, and if they do find it, help them eliminate it. I can also recommend that ChemSec makes hilarious videos like the ChemSec PFAS Rap Battle, which if you haven't seen, I encourage you to check out. Another thing that we're making is the 0PM Alternative Assessment Database, which is looking for alternatives for PFAS. So we took a lot of the data that was, and this is also Romain Figuer's work with colleagues at Stockholm University and Ian Cousins and others, Luc Miaz and Alina Sabadou. They made this great database where they would find all the uses of PFAS and try to collate all the replacement alternatives that could be explored. So this is a resource if you're looking for it to replace PFAS as well. And we also find through effective labeling, when people know about the risk of PFAS, it can really influence their consumer choice if they buy it or not, if they first are informed with what PFAS is, and if there's a label on that product showing that it contains a PFAS. So we can also do some better communication and market information to help drive the market away from these type of products and towards the alternatives, even though they might be more expensive. And also encourage investors to look for this type of, say, biodegradable, non-toxic chemistry. So there are some hedge funds out there that are investing in PFAS-free alternatives, and this would also encourage the market transition. Okay, so this is my concluding slide, and I'm looking forward to the Q&A, but to conclude that we have the tools now to transition away from TFA, to stabilize the exposure, and we like to prevent, prioritize, and remove in 0PM. So all you need to do this is love, and of course, and then transition to PFAS and TFA-free alternatives. Start with TFA precursors produced in the greatest volume, like the F gases and flufenacet. We have to prioritize, we have to classify and label TFA as a PFAS and integrate it in our PFAS reduction strategies. And if we have, and when the TFA that's out there, we should remove from the active emission sources, particularly around hotspots where industry is releasing them. With that, I'd like to thank you very much. And this is the paper and my co-authors, Andrea Gradelia, Juliana Gluga, Martin Scheringer, and Ian Cousins. And this is the funding that has been doing my project where I've been exploring TFA and other persistent mobile substances. And I look forward to the Q&A. Thank you.
Thank you very much for that excellent presentation. I think we've all learned a lot. There are many questions here, so we'll get to as many as we can, but thank you. I learned a lot. So it's a great presentation. So California, I live in California, and you talked about TFAs going into trees and to the leaves. And so when the forest fires happen, they happen here, they also happen in Brazil, they happen in many other places. Is TFA released when there are forest fires? Do you have any idea about that?
Yeah, I didn't get a chance to talk about that, but it's but I mean, we also look at if TFA is released by eliminated by fire, and it seems that under normal fire conditions, you have to get up to around 1,000 degrees Celsius to break down the fire. So if your fire is burning at 500 and 600, which is more typical for forest fires, it will be releasing the TFA, it won't be breaking it down. So in normal situations. And related to that, like there are heated situations where you can eliminate TFA other than 1,000 degrees, but you have to have the right catalysts to facilitate that. So it would release the TFA. Yeah.
So figure 1 of your paper shows lower concentrations of TFA in wastewater after 2010. Why might this be, or is this a function of the particular wastewater treatment plants?
Yeah, that's just due to the data availability. There was not a lot of data for TFA and wastewater. Some of the media we looked at, we had great time series, and those were the ones I presented, like groundwater and so forth. But the wastewater, there's very little time series. There's very little time series for soil and for sludge. Partly because those are trickier media. TFA is a tricky thing to analyze. When you have a chromatographic method, it kind of comes out with the salts. And so part of the reason why we have few data for wastewater and soil is that the more messy the matrix, the harder it is to quantify it. And that just hasn't been physically done. So definitely more funding on wastewater needed.
Mm-hmm. And is there an available method to test humans serum for TFA that's available for people on the ground that want to assess the level of exposure in different populations of concern?
That's a good question if it's done commercially. I know that there's companies that you can send in your own blood samples to get it measured for PFAS. I know a company that does this in Europe called Eurofins. I don't know if they include TFA. I don't think so yet. And there is actually a scarcity of TFA blood data. I would like to see more TFA blood data since it's such an important topic. But I mean, this is always really hard because getting the ethical requirements to do such tests is quite complicated and requires a lot of dedicated funding to get over those administrative thresholds. But it's very much worth doing, I think.
Absolutely. I hope it shows up soon because I think people will be really interested in that. And one of the things you mentioned in your paper was that 57% of the PFAS of 39 PFAS found in human serum was actually TFA, and that's pretty high. I think 57% would be TFA. Another question here, what are the major sources in China, India, and Asia overall? Have they been, I mean, we've seen some things from China.
Well, in principle, they would be similar. I mean, they're also using the same refrigerants that everyone else is. Like there can be variations in terms of what gases are produced, but I would say like yeah, well, something also that's just but that might be going a little bit in the weeds, but I could say it's largely similar. And when I was recently thinking about I was working with others about how pollution changes as developing countries develop. And that's something also to think about, that when developing countries develop, they might be able to, for instance, afford more air conditioners, and the market for these things like refrigeration technology increases, which is also contributing to the burden of TFA. But the actual industry sources are probably more or less similar, but there would be differences that are complicated. Yeah.
Yes. Okay. Then somebody else is asking, why does the US EPA describe TFA as a well-studied non-PFAS? Is that from lack of considering the science? Is there too much industry input? I know it's a sticky question, and I don't want to get yourself in an awkward place.
No, yeah,
You're
so
right.
I can claim ignorance on why the US EPA made certain decisions. I just know the existence. They have an existing their existing definition of PFAS, which they use in a lot of their documents, has a structural definition that excludes TFA. It has to have two. It has to have a minimum of two fluorinated carbons, and TFA just has one fluorinated carbon, and that's a critical difference. Why they call it a non-PFAS. Yeah.
And if all the emissions cease tomorrow, do you have an idea how we might expect stocks to develop over time purely from the breakdown of other PFAS into TFA?
Mm. Yeah, well, this is also that's a question that fascinates me. I'm trying the best clues I can get into it is seeing what's happening with the PFAS that have been largely banned, like PFAS. And like the good news there is that we see those work. We do see that PFAS concentration is decreasing in water, it's decreasing in blood. So this is another positive story showing that change can work. But ultimately it's just getting diluted. And so that'll get it diluted to a baseline. And there's and meanwhile while it's being diluted, there are of course stockpiles. There are contaminated military bases, there's contaminated airports that are slowly leaking for the next 100 years. So you're going to have this slow leakage of the existing stockpiles and this overall dilution, including to the deep ocean. But with TFA, it's a much more complicated thing because it's much more mobile and it's already widespread. And so I'm just wondering how effective dilution would be, and if we would see as marked an effect as we do with PFAS. Sometimes dilution is not a solution to persistent and mobile pollution.
Another question whether there's a species-specific effect. It was interesting that the effects observed in a rabbit were not observed in a rat study.
Yes, but yeah, that all depends on how the test is designed. So when they're doing their reproductive toxicity test, they're designing it different according to a different protocol than the rat study that was just done following another assay. Yeah, they don't find everything from the same type of study. They have to specifically design it from the beginning, and that's also the issue because there's so many organisms out there that we should be testing exposure to, but we just don't have the resources.
Yes, it's a lot of work there. Can you tell from a sample the origin of TFA? Is there any way to figure out in a given sample what the origin is and how much of the TFA in your wine came from atmospheric sources or pesticides, herbicides, etc.? So any way to figure that out?
So when it talks about like the forensics of TFA, that's interesting. Not something I looked into, but in certain cases you can deem that by the isotope ratio of certain products. So it might be so if you have a very sensitive technique that can look at the ratio of isotopes of carbon and fluorine, you can deduce that. I have not seen anybody doing that. The closest I can tell you is this study with on the atmosphere, where they're just seeing, just based on trends where the TFA is produced, that it's from a precursor, but it's really hard to say from what.
Okay, and then is the accumulation of TFA different between soil and water or atmospheric ecosystems?
Well, I think the best way to think of TFA is that it moves with the water. So when you have polluted soil, for instance, from application of a herbicide that degrades the TFA, it will wash down with the water. When we have it from the urban sources, it will go with the stormwater, and then it will go wherever the water flows. So that's just the best way. If you could just think of the water cycle, that's the TFA cycle, and where it accumulates is where would follow that path. Yeah.
These are really good questions. I'm trying to pull out the most relevant ones, but there are a lot, and I don't think we're going to get through all of them. Um, any evidence of enzymatic degradation of TFA?
Trying to think specifically of TFA. I've I've had like there are studies exploring enzymatic degradation routes for other PFAS. And I get asked about these a lot because they're like, could this be used, say, like for bioremediation? And my answer to that is this type of it's the same with the enzymatic breakdown of all PFAS and all persistent pollutants and all plastics for that matter. These are generally enzymes that exist that for microbes that need a very special situation to thrive, and generally not what you find in nature. If we lived on a planet where there was a lot of formation of PFAS naturally, I'm sure the microbial community on that planet would have evolved to degrade PFAS, but our naturally occurring microbial community did not do that. That being said, we can in the lab or in a chamber evolve a bacteria to get rid of PFAS, but that would only exist under very controlled treatment conditions in a chamber and not would not thrive in the environment.
Mm-hmm. You wouldn't have a list by any chance of the 23 US states that consider TFA to be a PFAS? Do you have any sense of that?
I do not know off the top of my head, but I'm sure one of the organizers of that letter that if you click on the link, probably one of the names in the top would know. Whoever was the first author on that. Yeah. Maybe I could also mention something that on degradation that we do discuss. There is a theory out there that some of the TFA is degrading, like a small amount, and that would be negligible, but it would be degrading to something called fluoroform through various pathways that under certain conditions, say under photocatalytic conditions. It might be a very small amount, but this might be important because has global warming potential. But that's just a theory that some people, I would also say that idea is out there, and there is interesting literature on that, but that's one pathway that I see being discussed, but that's the most famous one I know. But I'll hear the question.
Yeah, thank you. So I'll just read the question. I think what you've just said does address that. So the question was, have you found any biological degradation of TFA? Would that be conversion to HFC 23, or is
Yeah.
there any hope of degradation to benign products?
Yes, no, I will say that there are interesting theories out there that are showing that some TFA under certain conditions could do that. Yeah, I did not present that today, but because also I can also admit I don't really fully understand it, but I am looking at that and I'm seeing how that develops. Yeah.
Great, thank you. And yeah, I'll just pick out one other question here. The argument will be made that pesticides and pharmaceuticals are not large contributors to global TFA contamination.
Mm-hmm.
You shared some relative source information, but can you elaborate further on that?
Yes, okay. What I can say is to fully address that question, we need to know the mass of emissions. So we need to know exactly how much and the yields. So there might be we might have knowledge about how much F gases are made, and we would know therefore how much that would be contributing to TFA. With pharmaceuticals and pesticides, it can be trickier. Firstly, because we might not know, it might be an intellectual property, how much is made. We might not have access to that data, especially on a global scale. Some countries are more transparent about how much pesticides they're using than others, and pharmaceuticals for that matter. Also, we have to think about yields. So we know the yields, the F gases are quite well studied. We know which ones will make 100% TFA. A lot of the pharmaceuticals will vary. They might make between 7 to 20, or they'll make other things. They might not necessarily make 100% TFA. So then we also have to know the yield. So it could be tricky, but a place to start would be trying to get these mass quantities, and then we could address that. I would say, at least in the water context, because we use a lot with water, we can, in areas where we find hotspots, look for the sources that aren't refrigerants, because the F gases will more or less fall down with the rain. And so that gives everywhere this rain background that we can expect from that source. But when we see an area that has much higher concentrations that cannot be explained by that, way above this rain background, there's some local source there. And anecdotally, I think it's most commonly been monitored so far with herbicides, would be the explanation when we see these super high groundwater concentrations that come out of nowhere in the middle of nowhere. It's probably herbicides.
Mm. Any movement towards polluter pays?
On this front, I haven't seen it. But I can say a new development in Europe. They have this new urban wastewater treatment directive that targets the cosmetic sector and the pharmaceutical sector, that if what they produce, if that's spotted in wastewater, they have to help subsidize the cost or pay for the cost of the treatment to make sure that it does not exit that wastewater. So this is something that's brand new in Europe, and they're trying to see how they can implement it. But this would apply to the cosmetics and pharmaceuticals that are PFAS or TFA precursors.
Mm. So do you see a lot of NGOs or community groups in Europe rallying around to talk about TFA and try and find ways to shut it down, get rid of it, not use it, take it out of products and so on? Is there a lot of public awareness of TFA yet?
It's definitely increasing. I see a lot of it, and from the various sectors. I mentioned the chem sector and NGO, but I also see it from the Pesticide Action Network. They're worried about this aspect. The pharmaceutical NGOs as well, like HEAL, like you mentioned, one of your partners. They're definitely looking more into this. So, and it does take this sector-based approach that NGOs and scientists and industry working in different fields, because it's just a chemical that's relevant to many different interest groups. Yeah.
Seems to be very difficult to deal with soil. How would you treat soil that's contaminated with TFA?
Oh, well, it's funny you should ask, because we have a new research project where we're using that ability of the plants to take it up in terms of phytoremediation. So and the approach there is that for instance, if it's a farmer's field that you can't farm on anymore because of the PFAS pollution, that we first plant crops specifically for the goal of getting rid of these mobile PFAS. But then that plant is PFAS, so it has to be PFAS contaminated, so it has to be disposed of properly. So our suggested method is to pyrolyze it under conditions that would destroy PFA, and then you make this biochar, and then we'll till the biochar in the soil to soak up the remaining PFAS that doesn't go up the plant. And we're going to try doing this for some cycles to see if that will remediate the soil over some generations. We're very excited about it, and I'm glad I got the opportunity to pitch that new project.
Right. We'll have another webinar when you're ready to talk about it.
Yeah.
We all would like the answer to this question. So thank you so much. So we're just about the end of the hour, and I want to thank you very much for your research. It's really important. It's been an excellent presentation, and every question here starts with that excellent presentation. We want to know more. So thank you, and I think we'll be hearing more from many people that want to learn more about what we can do. This is creating a whole new atmosphere for which human beings have evolved. So what do we do now? It's again great to talk to you.
Thank you.
Thank you, Charles, and thank you so much, Hans-Peter, for sharing this important work. Thanks also to all our participants for your thoughtful comments and questions. I'll wrap up now with some quick announcements. A video recording will be available on Che's website soon, and you'll all receive an email with a link to the video. We encourage you to support the work of the EDC Strategies Partnership You'll find links to each member group on Chase Partnerships page. If you appreciate these webinars, please consider a tax-deductible donation to CHE, ANSESH, or any of these partners. Please also join us on February 27th for the next CHE Alaska webinar, Plastics, Chemicals, and Cancer, the role of the Global Plastics Treaty in preventing breast cancer. We'll share that link in the chat now. We also invite you to browse our website and those of our partners to find out more about emerging issues in environmental health science. With that, we'd like to thank you again for joining us. Thanks again to Hans-Peter for taking the time to talk with us today and Charles for moderating the webinar. And thanks to Rachel Massey and Kirsten Schaefer for their help behind the scenes. We hope to see you all again on future webinars.